Thank you. Do you have any homework questions? Question 1, section 7. Okay, this is the next main question. We're given a function defined by x times e to the x. Here we are. When you have a continuous function and you have a closed interval, the way we can determine the max and mean is to find a critical point, and we'll evaluate the function value at the endpoint and at the critical point, and then compare which one is the maximum, which one is the mean. So first, let's find out the critical point. Okay, so one find critical point. Right. By definition, critical point is when the derivative equal to 0 or when the derivative does not exist. This function, the function is defined by x multiplied by exponential function. Now, this function, both functions x and e to the x, they are defined for any x value. So there's really no region where the function could be undefined. So we don't have any undefined point. So the only thing we can do to find the critical point is to set the derivative equal to 0. So we'll find the derivative. I guess part of the difficulty in the calculation is to make sure the derivative is calculated correctly. You see there are two x. There's x in the exponential function. There's x in this function. So it's a multiplication, right? There's two x. So we have to do product rule. Using product rule to find the derivative, we have to differentiate one of the factor. For example, we differentiate the x, then the answer is 1, right? The derivative of x is 1. So we'll have 1 times e to the negative 9x. And that's one factor. And then you can keep the x. So you keep the factor x. But we're going to differentiate the e to the negative 9x. Exponential function's derivative is itself. So by formula, by differentiation of exponential function, you have e to the negative 9x. That's itself. That's the derivative of the exponential function. But we don't have e to the x. We have e to the negative 9x. So the negative 9x is an inside function. It's a composition function inside the exponential function. So you have to differentiate the negative 9x. Because according to chain rule, you still have to multiply the derivative inside function. So you still have to multiply the negative 9. All right, so the final answer for the derivative is going to be derivative is equal to e to the negative 9x. And here we have negative 9, and here we have negative x. So you multiply negative 9 with x, you will have minus 9x times e to the negative 9x. So in the way we write this kind of function, the tradition is try to write the number, the polynomial before the exponential function. So format-wise, make sure the way you write it is easy to analyze in your next step. Okay, so there. Once we find the derivative, we'll set the derivative equal to 0. Like I said, this derivative equal to 0 is how we're going to find the critical point in this case. Then how do we solve this? Now we've got equation. How do we solve this? How do we solve this equation? You see the e to the negative 9x? It's in here and it's in here, right? So that would be if it's in both factors, it's a common factor, right? So we can factor the e to the negative 9x as a common factor, And then everything else is what's left in the parentheses. So the first one, without the e to the 9x, you have 1. So the other factor, let's multiply e to the, it's 1. And for the other one, we have negative 9x. Without the e to the 9x, you factor e to the 9x out, and you have negative 9x. So you have negative 9x. So that's what we have. Factor the left side of the polynomial, left side of the derivative, left side of the equation. We have this. And then what we're going to do is, well, the reason we want to factor a common factor is in the hope that we will turn a big equation into smaller equation. So find equivalent representation of the equation. So now this equation becomes two form, and one is 1 minus 9x equal to 0. I mean, when two number multiply equal to 0, one of the factor has to be 0. So see, this is a 2 factor. E to the 9x, negative 9x is a factor. 1 minus 9x is another factor. A times b equal to 0, then either a equal to 0 or b equal to 0. And that's the reason we say, if you see a factor that equal to 0, factor multiply equal to 0, then you can now look at each factor and make sure you solve the smaller equation, setting the factors equal to 0. See, I'm writing this equal to 0, but I did not write e to the negative 9x equal to 0. Exponential function, they were never equal to 0. So e is a positive number. E to a negative power only means that the negative power is not negative. It's still positive. It is a reciprocal. Remember, when you have something to a negative power, that means it's 1 over a big factor in the denominator. So that is definitely a positive number, which will never equal to 0. So out of these two factors, that's a positive number. This could be a number that equal to 0. This could be the reason 1 minus 9x is the reason that this whole equation can equal to 0. So solve this, we end up having x equal to 1 over 9. All right. So this function has only one critical point. That is at 1 over 9. See, our interval is 0 to 2, and our critical point is 1 to 9, 1 over 9. So second step of the whole method using derivative to find max and min, which is evaluate the function value, or evaluate the y value. So then we will see which one is maximum, which one is minimum. So we're going to make a table. And we do what we were talking about yesterday. We make a list of all the possible x value for the max and min, and we calculate each of their y value. So here is our x value. In your list of x value, you have the endpoint 0 and 2. We have 0, we have 2. That's from the interval of the question that was given. And then in the middle, we're also going to lay out the critical point that we just find, 1 over 9. And now here we're going to go ahead and find the y value. The way we can calculate the y value is using the original function definition. Number 1 is when it's equal to 0, you can see 0 times e to the negative 0. 0 times anything is still equal to 0, so the y value equal to 0 in that case. And then for 1 over 9, it looks like this. It's going to be 1 over 9 times e to the negative 9 times 1 over 9 is negative 1 power. Right. So 9 multiply 1 over 9. 9 times 1 over 9. 1 over 9 is 1, so power is negative 1 now. That's that one. I don't know the value. You'll have to use a calculator to see how large it is. Since the power is negative 1, so I know that's 1 over e, and this is 1 over 9. So the 1 over e times 1 over 9 probably is a really, really small number. Then we have 2. If x equal to 2 is 2 times e to the negative 18. It looks like an even smaller number. Whenever the power is negative a large number, that makes the number really small. Okay, so now it's time to evaluate which one's maximum, which one's minimum. I mean, the way I write it, we can hardly compare them, so you might have to find the decimal answer to say which one's largest, which one's smallest. I know obviously 0 is the minimum because both of these two are positive. Like I said, e to a power, it is positive. So positive times positive, they're all positive. So for the other two values, which one is the maximum? That's the question. Because we already knew the minimum has to be the 0. Which one's maximum? Do you guys do some calculation? Which one's minimum? It's two numbers. Which one's small? You know, maximum. Which one's bigger?
So 1 over 9 to the negative 1.
Okay, so 1 over 9 is biggest. So here we have it. This is the maximum. This is the minimum. This is 0, and all the other two they're positive. So we'll say the minimum is equal to 0. It happened when x equal to 0. The maximum is 1 over 9 times e to the negative 1. I guess that's how you enter into WebWork. And here is the x value. That's when x equal to 1 over 9. So this is pretty much how we enter into WebWork as our solution. Stephanie, did that answer your question? Any other questions? Any other questions? Other more questions? So that's that from 3.2 homework. Now today we were gonna talk about 3.3, and like I said in chapter 3, we're trying to utilize derivative as a way to look into a function, look at a lot of detailed behavior of the function. So for example, using the derivative, you can find the max and mean for the continuous function at a closed interval. That's section 1. Using the derivative, you're going to find a special point at a closed interval where the slope is equal to the average slope of the function. Now, section 3 will have our increasing, decreasing behavior. And first, yesterday we defined the increasing, decreasing of function using comparison of two given values, like a is less than b, so which means a is on the left, b is on the right. So suppose f of a is less than f of b, so the one on the right side tends to be higher than the one on the left side, and this means the function, if that's always the case, then this means the function is increasing. And the other definition says a is on the left of the b. If the one on the left has a higher y value, that means the function is a decreasing function. So, and visually, I mean, we draw the graph yesterday. Visually, you can identify the functions increasing, decreasing, but by just walking along the curve from the left to right. If you feel like you're walking uphill, then it's an increasing function. If you walk along the curve, if you feel like it's a downhill walk, then it must be a decreasing function. So those are increasing, decreasing definition of a function. And then we talked about how do we use derivatives to determine increasing, decreasing. Now, if the function derivative is positive, then the function is increasing. If the function's derivative is negative, then it's decreasing. So we definitely want to know if the derivative is positive or negative in order to find out increasing, decreasing. All right, so the plan would be now, instead of finding where it is positive, where it is negative, we definitely have to find where it is equal to 0. Because other than the part that equal to 0, on all the other parts, on all the other points, it's either positive or negative. So we're going to single out the one that the derivative is equal to 0. So number 1, we want to find a critical point where the derivative is equal to 0 or on this line. Number 2, we're going to use a critical point to separate the domain, separate the interval into smaller intervals. Number 3, each of the interval, we want to know if the derivative is increasing or decreasing. If it's positive, then it's increasing. If the derivative is negative, then it's decreasing. So that's the plan. All right, so let's look at example and see how the plan works out if we really want to know the increasing, decreasing behavior of a function. And this is the most big assignment for section 3 is, so let's try this method. All right, let's see. We'll follow the plan, the procedure that we read in the text. So step 1, we're going to find the critical points. This is similar to section 1. Find a critical point of the function, which is basically letting the derivative equal 0 in this case. By definition, could also include when the derivative does not exist. In this case, it's a polynomial. The derivative always exists, so we don't have to worry about the second possibility. All right, so we're going to find the derivative, and we're going to set it equal to 0. What's the derivative of the function? Stephanie, what's the derivative? What's the derivative for x? Yeah. What's the derivative? Power rule. What's the derivative?
3x squared plus 2x minus 1.
Okay. 3x squared plus 2x minus 1. So that's the derivative. And we apply power rule. Power rule says if you have a power function, the derivative function is power goes to the front and the power minus 1. So power 3, move the 3 to the front, and then power 3 minus 1, so that's 3x squared is derived from x squared, from x cubed. The x squared power 2, so you move the 2 to the front, and then power minus 1, so that's 2x. And negative x, the derivative, you move the power to the front, negative 1. And then the power minus 1, 1 minus 1 is 0, so power 0, and that makes it a number. So now let's find the derivative. We're going to make this equal to 0. We hope to find solution for this degree 2 equation. Remember, this is a quadratic equation, degree 2 polynomial. The solution should be 2 solutions. But the way we find the solution, you can do quadratic formula, you can do factoring. Normally factoring, if it's available, it would be a little bit faster than the quadratic polynomial. So I'm going to factor 3x squared. 3x squared equal to 3x times x. All right. So this is factor 3x squared, which equal to 3x times x. We also need to factor the negative 1. Let's see which way it works out. So for example, we can do negative 1 times a positive 1. Let's see if that works. So 1 times negative 1 is a negative 1, right? So we factor the last number, we factor the highest degree, and then to say if the coefficient works out for the middle term, for the degree 1 term. So that's negative x, that's positive 3x, together that's 2x. So this is the right factoring. Any questions? All right. This method doesn't work for all the degree 2 polynomial. It works for this one. It works for some scenario, but doesn't work all the time. All right. So now we have the factoring. Now we set the 3x minus 1 equal to 0. That's one factor. We can also set x plus 1 equal to 0. That's our second factor. Just so we would be able to find both of the solutions. So 3x minus 1 equal to 0. You move the 1 over to the right side. You have 3x equal to 1, divide both sides by 3. So x equal to 1/3. It's one solution. The second case, if x plus 1 equal to 0, you move the 1 to the right side, return it into negative 1. So x equal to negative 1 is the solution for that part. So x equal to negative 1. And now we find two solutions. We find two solutions for the polynomial. And those two numbers are going to be labeled on the number line. And we are going to do what we call partition of the domain. The polynomial is well defined on the entire interval. So step 2, we're going to really identify, determine the interval. All right. So here, find the interval on which f is increasing or decreasing. So you have to have the interval, then determine on each interval whether it's increasing or decreasing, right? So what I recommend is trying to draw a number line which should represent your domain of the function. All right, on the number line, that's from negative infinity to positive infinity. Because this function is a polynomial, so there's really no requirement for the domain. So our domain, this is positive infinity. On the left, far left is negative infinity. Right in the middle, we're going to label these two numbers. As you label the number that you find, the critical point that you find, you want to label the negative number, smaller number on the left and bigger number on the right. So we're going to label -1. Let's see, that's -1. And we're going to label this as 1/3. Okay, so these two critical points are like knife. Right now you make two cuts. 1, 2. Two critical points. You make a two cut of the whole number line. And that's cutting the entire number line into 3 parts, right? So that's 1, 2, 3. The one on the far left is the interval -infinity to -1. All right, so that interval, the -infinity to -1. And then the one in the middle is -1 to 1/3. That's our middle interval. We're creating 3 interval, and the one on the far right is 1/3 to positive infinity. So basically, the second step is to allow us to figure out how many intervals are we talking about. I mean, you said find the interval or function increasing or decreasing. Where exactly are those intervals? How do I know what interval do I need to use? So basically, the interval you're going to decide is dependent by what was the domain, which in this case is negative infinity to positive infinity, and what was the critical point. So critical point and domain combined together is how we determine the intervals. Any questions? All right. And now we're going to look at step 3. All right, now we know the interval. We are going to look at increasing, decreasing behavior. So increasing or decreasing? That was a question. So for each interval, you can only be, it's either increasing or decreasing. You cannot be both on the interval that we just decided. Whether it's increasing or decreasing depends on the derivative, right? So the one that's increasing must have positive derivative. The one that's decreasing must have negative derivative. So remember, this is on the increasing interval, the derivative is positive, and the one that's decreasing, the derivative is negative. So all we have to do is to figure out a couple of points on those intervals, which allows us to determine whether the derivative is increasing or decreasing. So we are going to evaluate the derivative function to see if it's increasing or decreasing. Any questions so far? So remember this time, we are also going to evaluate, but we're not evaluating the y value. We're evaluating the derivative, the y prime to the one way to say. All right, so we're going to evaluate f prime this time. Since f prime being positive or negative, it's gonna tell us whether it's increasing or decreasing. All right, so here we're gonna look at each interval. So for example, for a negative infinity, the first interval, negative infinity to -1, okay? And we want to know if it's increasing or decreasing. So we're like, let's pick a point. On this interval, what is it in this interval? We can calculate, let's say, -2. So we can calculate a value f prime of -2. All right, so I want to see if it's increasing or decreasing. So since the function equal to this, so I'm going to plug in -2 in here. So the calculation for it is going to be 3 times -2 minus 1, and then times -2 plus 1. All right, I'm using, see, this is a factor form. I'm using the factor form as a way to determine whether it's increasing or decreasing. It turns out it's -7 times -1 is +7. So and it's positive, all right? So I know on this interval, the function is increasing. So I'll just write increasing. All right, because it's positive, so it's increasing. Any questions so far? And we do the same for the other two intervals. For -1 to 1/3, we can calculate the value, say, at 0. I mean, 0 is between these two numbers. You plug in 0 to this function, you have -1, which then is negative. That means the function is decreasing on this interval. And the last interval is 1/3 to positive infinity. And we can pick any number just so we would be able to double check. We can calculate what happened at 1. I mean, 1 is between 1/3 and positive infinity. At 1, it's 3 plus 2 minus 1, which is 4. So it's positive, so that's why how we know this is increasing. So it's increasing on the third interval. Any questions? So the interval that the function is increasing is -infinity to -1 and 1/3 to positive infinity. The interval where the function is decreasing is -1 to 1/3. That's where it's decreasing. So that way we can label each interval about whether it's increasing or decreasing. And I finished solving the increasing interval for the function. Any questions? So that's the solution for this one. And we follow what we're talking about, the procedure over here. Step 1, 2, 3. All right. So what we were doing here is what we call the first derivative test. Because f prime is the first derivative. On top of that, we can calculate higher grade derivative, like second derivative, third derivative. And that's why the one we are doing right now is called the first derivative test. We just want to know, sometimes we want to know if the function has a maximum or local maximum at a point. So here it says, suppose you find a critical point, which is C. Suppose you find a critical point that is C, and then you can look at the value around the C. So number one, if the derivative is first negative, first positive, then negative at C, then C must be a maximum. And second one saying that if the derivative is negative, then positive, then the function must have a minimum at a point. And this third one is saying if the function did not change sign, it's negative before C and negative after C, or positive before C and positive after C, then it's not a minimum or maximum at all. So this is a so-called first derivative test. Why do we have that test? Because a lot of time we have a critical point, but we're not sure whether it's a max or mean. So the first derivative test made it possible for us to determine if we have max or mean. A visual presentation, like visually imagining what's happening, might explain why we have the first derivative test. All right, let's say you have a critical point, critical number. Suppose the derivative turn from positive to negative, so it's increasing. I mean, derivative positive means increasing, negative means decreasing. So this is when the derivative is positive, and this is when the derivative is negative. So then we see in the middle, this one, at C, this f prime of C, the f of C, must be a local maximum. This is the rule number 1 for the first derivative test. Second rule number 2, it says if the derivative turn from negative to positive, means that it's decreasing, and then positive, this is when the derivative is positive, this when the derivative is negative, and then what we have here is a minimum. and that's a c that will happen at c. So if before c it was negative, after c is positive, then at c it must be a minimum, and that's rule number 2. Now rule number 3 is saying that if it did not change, if the sign of the derivative did not change, what do we mean? It means that it's decreasing and then decreasing, or if it's increasing and then increasing, such as the cube function. So this is when the derivative is positive before c and positive after c. This is when the derivative is negative before c. That's the point is c. And then negative after c. So if it's the same thing, same sign, did not change sign, then that obviously the c is not a minimum and it's not a maximum. There's not it basically did not change direction, so the curve did not change direction, therefore we don't have maximum. That's the first derivative test, which is a way to tell if we have maximum or minimum. Do you have any questions? Any questions? I mean, sometimes you might find the derivative that equal to 0. You may ask yourself, here I have the derivative equal to 0, I have a critical point. Do we have a maximum in here? And sometimes, if you see the graph, it's easy to see. I mean, if the graph seems to be hover, it's higher than any other point, that's maximum. If it's lower than any other point, it's minimum. But in reality, a lot of times graphing is difficult, especially if you have a complex function. So we want to compare the derivative to tell us a quicker decision. So analyzing the derivative's value sometimes helps, and that's why we have first derivative test. The test, I mean, whatever conclusion that you're calling the test, because test tells you positive or negative, it tells you a conclusion affirmative or not affirmative. So do we have a maximum or do we not? So through this test, we will be able to tell that. We're going to be able to decide if we have a maximum. And with this, okay, look at the question. All right, so here is the question that we want to find the interval where it's increasing or decreasing, and then we want to see if we have maximum or minimum at the point. So here, I mean, this question is pretty much the same as the first example, except now we are able to find more. Using the first derivative test, we can tell if we have a maximum. I'm going to use this one as an example. All right, we are going to do exactly the same as what we did for the other question. On top of that, we're going to also determine if we have max and mean. And here we have the function. So we're going to follow those steps we had talked about before. Step 1 is we want to be able to find the critical point. All right. Remember, by definition, to find the critical point, you have to find where the derivative equal to 0, or the derivative does not exist. There's 2 types of critical points. Whichever critical point, whichever type of critical point we're trying to find, we have to find the derivative first. Now, this is a slightly harder question because we don't have a polynomial. This is actually a rational function, and we got a division in here. So to find the derivative, we'll have to follow the quotient rule. Do you remember what was the quotient rule?
The derivative of h times g minus derivative g times h over t squared.
Right. Thank you. So by quotient rule, we have, I can write the quotient rule to the side. All right. Quotient rule says if you get a division, h over g, and to find the derivative, you would square the denominator and differentiate the numerator times the denominator minus differentiate the denominator, multiply the numerator. Right, so this, for our case, we'll square the denominator, which is x minus 1 squared, and we'll multiply derivative of the numerator. Derivative of the numerator is 2x, so we have 2x times the denominator, that's the x minus 1, and then minus the derivative of the denominator, which is equal to 1, and multiply it by the numerator. Okay, so apply quotient rule, we find this is our derivative. We need to calculate things in this case, so we cannot let it be this case. We have to simplify it, so it's easier to solve the critical point. So now our derivative looks like this. The numerator is going to be 2x squared minus x squared, so it's distribute the 2x, so you have 2x squared minus 2x minus x squared minus 3. And this is all over x minus 1 squared. Okay, and so we're going to try to simplify the numerator. We have 2x squared minus x squared, then you have positive x squared, so we have x squared minus 2x minus 3. This is over x minus 1 squared. Okay, let's see if we can factor the numerator. It's x minus 3 times x plus 1 factored. Minus 1 squared. All right. The reason I factor the numerator is because I want to make the derivative equal to 0. So, and we solve these two different scenarios. If you have a derivative equal to 0, that means you're gonna have the numerator equal to 0. If this fraction equal to 0, then we must have x minus 3 times x plus 1 equal to 0. Okay, with this we solve two solutions, x equal to 3 and then x equal to negative 1. Any questions so far? That's those two. And then we also have when it's undefined. This is the division, so we do definitely have the and E point. It is undefined when obviously division by 0 makes it undefined. So x equal to 1 is when it's undefined. Okay. The original function. Now this is step 1. So step 1, we did all the necessary computation. We really analyze the derivative to its basic. We find all the important points for the derivative. And this is going to be the building block for the step 2, which is creating interval. So step 2. We're going to find intervals. Right, so see the question says find the interval where the function is increasing or decreasing. So you're going to have to create interval. Where do you get interval? You're going to have endpoint for your interval. So we find a critical point, we determine the domain, so all these, it's in the hope that we're hoping we'll be able to find our interval. So how do we find the interval? We'll draw the number line as we did with the other example. But in this case, the number line is still it's slightly more complicated because we have a division. So the division limited the domain. In the domain of this function, we have to say by definition, the domain of the function x cannot be 1. You have to take away the number 1 from the function because if x equal to 1, you would not have a y value, right? So 1 will be like the forbidden point because if x equal to 1, we don't have a computed y value for it. So in the domain, we take out a number I guess we should have an empty point at 1. So 1 would be a problem. That's 1. All right, and that's 1 point we have to take out. And then we have negative infinity to 1 and 1 to positive infinity. That is already separating the entire interval into 2 parts. So we have negative infinity. We still mark it out that because it's going to be part of the endpoint. And then we also have, so that's part of the point that we find in step 1. We have 1, we have negative 1, we have 3. As you try to label all these points on your number line, make sure they are ordered from left to right, small to big. So we are labeling, over here we have negative 1. Over here we have positive 3. So all the points that we find out in step 1, the 1, the 3, the negative 1, they're all labeled right here. So the 1 is special. 1 is when it's on the sign, which means 1 is the one that we're forbidden to take out value from 1. All right, so I often start drawing a line at a point that now it's going to cross by. So we'll draw a line there just to tell us that, hey, that's not using any number here because these two has an invisible wall. So these 2 parts, they're not supposed to be connected. So I'm drawing the line at 1 so then we can tell that it's not cross the line. That's the line between the 2 parts of the graph. All right, so now we can look at interval. The interval that we find out, so they were, using the number that we find out in step 1, like 1, 2, 3, same number. The entire line, we made 1, 2, 3 cuts. If you got a line and you cut 3 parts, you end up having 4 parts, and therefore you have 4 intervals. So we're going to label all 4 intervals. Those are the intervals that we find now from step 2. So negative infinity to negative 1 is 1 interval. Negative 1 to 1 is our second interval. 1 to 3 is the third interval. 3 to positive infinity is the fourth interval. So step 2, find the interval. Don't have our interval. Any question? Question? Now let's see step 3. 3 we are going to find increasing and decreasing. So we're going to try to tell each interval, is it increasing? Means the derivative is positive, or is it decreasing? Means that the derivative is negative. So we're going to ask those questions. So we're going to do that by looking at each interval one by one. So for example, we're going to start with the first interval. That is negative infinity to negative 1. All right, we're going to see if it's increasing or decreasing. So how do we know if it's increasing or decreasing? We need to know the derivative. So let's see. Derivative f prime. Well, your derivative has to be based on a certain computation. So I'm going to pick a number between negative infinity to negative 1 anywhere. Infinity is fine. So it really doesn't have to be specific. So I'm just going to pick, let's see, negative 5. Just pick an easy number in that interval. So if I see 1 and negative 5, you see which calculation we're going to use. Let's use this one. This is an easier computation. So to make the computation easier, I'm going to do this calculation. So I'll say negative 5 minus 3 is negative 8. Negative 5 plus 1 is negative 4. So negative 8 times negative 4, 32. And 32 divided by negative 5 minus 1 squared, 36. So 32 divided by 36, that's what it is. I mean, really what's important, whether it's a negative or positive, the exact value is okay. So well, we know that it's positive, so we know it must be increasing in here. So then on the interval would be increasing. And you can also go ahead and start drawing on the curve. So it would kind of tell, like, on this interval we got increasing. What do we mean by increasing? Increasing. That's what it means. So I start drawing the on the little graph there, just so that you know what this increasing means there. Maybe my graph isn't that. It's increasing, but I feel like it's negatively increasing. All right. Any questions so far? All right, so we do the same for every interval. For example, the second interval is from -1 to +1, and then we can do the same. We want to find out if it's increasing or decreasing. The way we find it out is to calculate the derivative. I mean, -1 and +1, one of the middle number, one of the number is 0, so we pick 0. You're going to calculate what happens to the derivative if x equals 0. I mean, if this is 0, so 0 minus 3, 0 plus 1, so it's -3 over 1. And you see it's -3. This is negative, and we know it's decreasing. So the function is decreasing on the interval, so visually you're going to draw a decreasing tendency over here. See what's happening? Increasing and decreasing. See that invisible wall there? The reason I draw it there is because when you draw like a hypothetical graph of your function, you kind of know that the invisible wall is going to stop it here from passing to this. So right there we have increasing then decreasing. We have a maximum at -1. So -1 is a location where you see a local maximum of your function. Any question? All right, we should do the same for the rest. I feel like I'm out of space here, and the third interval is supposed to be the 1, 2, 3. Interval 1, 2, 3. And I can pick an easier number. A number between 1, 2, 3 is 2, so you can plug in 2 to your derivative function. If you plug into 2 minus 3, it's -1, 2 plus 1. It's also negative. 2 minus 1 is 1. -1 times, it's -3. So -3 also, and that makes it negative. That means it's also decreasing on 1, 2, 3. So from on the interval 1 to 3, this is actually decreasing. But if you plug in 2 in here, 2 squared plus 3 is 7, 2 minus, so 7 is actually positive at 3, 1, 2, 3. If you plug in 3 minus 1 is 2, 12 over 2, 6. So it's decreasing. 7 to 6 is decreasing. So it looks like it will be decreasing here. Right. So I mean, try to imagine what's going on. I mean, this 1 is invisible wall. So this is a asymptote. When the denominator of the rational function equals 0, this behaves as an asymptote. So the entire function, and -1 is stop it. So then you have 2 separate parts. One is for the left side of -1, one's for the right side of -1. There are 2 separate parts of the graph. Any question? So increasing, decreasing, and then decreasing. I'm guessing it's increasing again, but you can confirm that by your own calculation. The last interval is interval 3 to +∞. Again, if you want to confirm increasing, decreasing, you would try to pick a number. What number do we pick for like verify increasing, decreasing?
4.
So it's 4. All right, so we're gonna plug in 4 to the derivative function. I take the one I blocked out. So 4 minus 3, 4 plus 1, that makes it 5, and 4 minus 1 is 3. 5 over 9. So then the answer is 5 over 9, which then is positive. So we know it's increasing. Not a big increasing. I mean, the slope is not big, but it's still positive, so it's still increasing. So then that makes this a local minimum, right? Decreasing and then increasing, so this is a minimum point. Visually, the minimum point is a point that's lower than all the other points. around it. So you can see in a small local region, this is a higher, this is a higher, this is the lowest point. And this is the highest point locally on the curve. So there we have it. We have local maximum, local min, local maximum -1, local minimum S3, and we also have increasing, decreasing interval already labeled. And I finished solving the entire question. Any questions? Are you okay? Were you able to follow through? Do you have any questions? Any questions? So that's this example, which involve a first derivative test to explain max and mean. And it also involves sign analysis to explain increasing and decreasing. And this is what's the main point of the section 3, that is being able to analyze a function using the derivative. All right, let's see, we can look at a couple of practice questions on the set. Can you assign the assignment? Sign this before so you can actually visibly see it when you log in. Alright, so you can log into your section 3 to see your questions. There are 10 questions left assigned. Start with the first question. Alright, so this is a homework assignment on WebWork, question number 1. So let's try to use this as an example, another example. And then after that, we're going to do, like her question, we're going to do a practice question. Here's assign homework. Okay, so the question says we want to find the open interval where the function f is increasing. Then determine the coordinate of the relative maximum or minimum. So 1 is what was the interval where it's increasing, 2 is what was the interval where it's decreasing. Third question is what was the local maximum, and then fourth question is what was the relative minimum or local minimum. So we're going to follow what we're talking about. You do analyzing the derivative sign, and you're going to analyze the interval. Then you're going to analyze whether we have a maximum for the whole function. All right. So first, let's find the critical point. Step 1, we're going to find the critical point, which means we're going to set the derivative equal to 0. Of course, if the derivative has any undefined point, we'll be able to analyze it. This is a polynomial. It is always well defined, so we don't have to worry about D and E. So a derivative is 4x minus 16. 4 times 4, 16. And then power minus by 1. 4 minus 1 is 3. So the power should be 3. That's our derivative. Any question? So again, we don't have any D and E. We have derivative equal to 0. So we're going to let the derivative equal to 0 and try to solve for the x value. After that, let's say this is a polynomial, equation of polynomial that's equal to 3. So this equation is supposed to have 3 solutions. So we need to find 3 x value. And those 3 values are going to cut the number line into 4 parts. And that means we're going to find 4 intervals. So step 1, we're going to try to find those values, and this value is going to be the building block for our interval. So we're going to factor 4x. the 4x has 4x and 16 also has 4, 16 also have x. So 4x is a common factor. To factor the 4x out of it, you see the 4x, if you take out the 4x, you're left with 1. Okay? The 16x cubed without the 4x, you still have a 4. 4 times 4 is 16. Without the x, you still have the x squared. So we have x squared. This is after the factoring. Any question? So factoring. After we factor, what do we do now? Well, the reason we want to factor is because we can simplify the equation. We want to solve a smaller, easier equation. That's the whole point of trying to factor. What's the next step?
Would you use the negative 4x squared plus 1 instead of equal to 0? Because for the other one where we said a times b equals 0, 1 has to be 0.
Right? Yes. So the 4x equal to 0, right?
Right.
So we have 4x equal to 0. And we also have the second part, which is that 1 minus 4x squared equal to 0. So basically, the factoring allows us to write a big equation into two smaller equations. Now, the first one, if 4x equal to 0, what is the solution?
0.
0, yes. So for the first one, the solution is x equal to 0. Now, for this equation, what was the solution? How do we solve it?
Would add subtract 1, divide 4, square root.
Okay. So we could subtract the 1 and divide both sides by 4, or divide by negative 4. Negative 4. So we divide both sides by negative 4, then x squared will be by itself, then x squared equal to 1/4. Let's divide both sides by 4, by negative 4. And now what else?
Square root both sides.
Square root both sides, which is?
Square root.
What was the root of 1/4? What is root of 1/4? Root of 1/4.
1/2.
1/2, yes. This is figure 2, so we actually have two solutions. X equal to 1/2 or x equal to negative 1/2. That's the solution. So this entire process, letting the derivative equal to 0, allows us to evaluate degree 3. So degree 3 equation is supposed to have 3 solutions. So we get 0, 1/2, negative 1/2. So that's the solution. So now we are making 3 cuts of the entire interval. So step 2, I'm going to find the intervals. So where do we find the interval? We find it in the number line. So we'll draw the entire number line. This is a polynomial. There's no additional requirement. So a number line we draw from negative infinity to positive infinity. The left endpoint is negative infinity. The right endpoint is positive infinity. We're making label 3 number in order: small, bigger, and biggest of the interval. So then we have 0, we have 1/2, we have negative 1/2, negative 1/2. All right. Think about this as a stick. So you got a stick and you make 1, 2, 3 cuts in your stick, and then you're cutting the whole stick into 1, 2, 3, 4 parts, and each part is an interval. So the interval that we find out using all these numbers that we labeled, you have negative infinity to negative 1/2. That's the first interval. Then you have negative 1/2 to 0, and then we have 0 to 1/2. And the biggest one is 1/2 to positive infinity. That's the 4 interval that we find out. And then on each interval, we need to know increasing or decreasing. So 3. The last step, we are going to try to figure out increasing or decreasing. And these are going to be determined by the derivative, positive or negative. That's the question. So on each interval, we're going to answer the same question. Now this, like the first interval is negative infinity to negative 1/2. To know if it's increasing or decreasing, we're going to find a derivative value on the interval. What would be an appropriate point to test on this interval? Let's pick a point from negative infinity to negative 1/2. What do you want to use? The interval is large enough. What would be? Negative 3. So we're going to do negative 3. All right. Whichever one is fine. I would recommend using this because it's factored. It's a little easier to calculate. So when we do that calculation, we'll have 4 times negative 3, and then times 1 minus 4 times 3 squared, which is 4 times 9. And you can see it's negative 12 times negative 48. Whichever was the answer is positive. So we know it's increasing on this interval. You can double check with your calculator. Negative 12 times negative 48. Not 48. 4 times 9 is actually 36. My fault. It's negative 35. You can also calculate using your calculator, which makes it more reliable. Okay, but I know for sure that's increasing. You can also, let's move on to the next interval. That was negative 1/2 to 0. But at least I know it's increasing now. 1/2, 4 times 1/2 is negative 16 times. What was it? 4 times 1, negative 1/2 is negative 2. 16, 0. So it looks like this. Try to graph it. You can also graph it with a grapher, but I just want to indicate it. I realized at 1/2 you can calculate original value. Okay, 1/2 and 1/2. Negative 1/4. That's 1/4. Positive 1/4, negative 1/4. Yeah, it's a 0 at this point. I'm trying to try to make sure I didn't. I want to figure out whether at this point it's positive or negative, and then I realize it's 0, and then 0 and increasing right there. All right, so that's the first interval. Second interval from negative 1/2 to 0. Again, we need to find a way to test it. So we're gonna have to find a point. What would be a point to use? Negative 1/2 to 0.
Negative 1/4.
Negative 1/4. So do negative 1/4. All right, again, we're going to use this as our calculation. So 4 times negative 1/4 is negative 1. So it's negative 1 times 1 minus 4 times 1/16, which is 1/4. Okay, so you can see it's negative 3/4, which is definitely negative. You can also use your calculator, of course. Because it's negative, we know it's decreasing. So now it's decreasing, increasing and decreasing, but it's decreasing down to 0. Maybe I was wrong. I'm trying to think of it. Maybe it's this way. So anyway, increasing and decreasing. We can go back to the original graph to kind of see what it is. Because it's increasing then decreasing, I know at the negative 1/2 we have a local maximum. It's part of the question, so I try to label the maximum there. So that's our second interval. Any questions so far? This is not very accurate, but I just want to show the tendency, increasing, decreasing. The third interval is 0 to 1/2. So again, we're going to calculate the derivative to see if it's positive or negative. What point do we use? 1/4. So we're going to do derivative value at 1/4. Again, we're going to do this calculation, the block, this calculation. So we'll do 4 times 1/4, which is positive 1. And then 1 minus 4 times 1/4, 4 times 1/16, it's 1/4. And we end up getting positive 3/4, which is positive, so we know it's increasing. All right, so in this interval, it's increasing. So right here at 0, we must have a minimum. Yeah, local minimum. Last interval is from 1/2 to positive infinity. And we can test a point. Which point do we test?
1.
1. All right, so we'll do 4 times 1, which is 4. We're testing the derivative value. And it's 4 times 1 minus 4. And that's negative 3 times 4. So it's negative 12. That's negative. And that's how we know it's decreasing. So in this interval, it's decreasing. Therefore, this must be a local maximum. Now we can start answering the original question. We have increasing interval. They were negative infinity to negative 1/2. The other increasing interval is here, 0 to 2. See, this is also increasing, and so 0 to 1/2. You can also see it on the graph. The decreasing interval is from the negative 1/2 to 0. This is decreasing. This is also decreasing. So you also have 1/2 to positive infinity, which we label as decreasing. So that's increasing and decreasing intervals. So we mark out the interval. Local maximum, we have 2 maximum. They are at negative 1/2 and positive 1/2. We have a minimum that happened at 0. Is that one? All right. This finish answer the entire question for problem number 1. Do you have any question? Any question? All right, you should have something similar. Do you have an identical question or do you have slightly different question?
Yeah, slightly different.
Okay. All right. We can also graph the function to tell if we had the right conclusion. One of the ways to steal the answer is graph the whole thing. So we got y is equal to 2 times x to the power 2 minus 4 times x to the power 4. Let's see. 2 times x to the power 2 minus 4 times x to the power 4. There. Let's see. This is what's happening. So here we have a local maximum. These are local maximum. Here is a local maximum. Here is a local minimum. And then the rest, they are just increasing, decreasing. So increasing, decreasing, increasing, decreasing. So that kind of, the graph itself kind of verify what we have calculated in the analysis of the derivative there. Okay. Sketch is really rough, but at least the increasing, decreasing, decreasing. Any questions? Let's see, it looks like we don't have a lot of time to do one more question. Done that question already, and this is the only question that we might be able to work out. All right, let's try this question, see if you are able to identify the local maximum. What we're going to do is we find the derivative, and then we set it to equal to 0, and then we will see whether it's increasing or decreasing. Once you know the increasing, decreasing, you probably will be able to identify where it has local maximum or local minimum. Oh, you already have your solution? That's right. Yeah, so I find the two critical points. So basically, there are 0 and 2. You have negative infinity and positive infinity. Now you have 3 intervals, 0 to negative 0, 0 to 2, 2 to infinity. And now you need to know whether the derivative is positive or negative. From this negative into 0, you plug in -1. And it looks like it's positive. So it's positive in here. 0 to 2, you can plug in 1. It looks like it's negative 2 to infinity. You pick a bigger number, it's positive. So the whole function goes increasing, then decreasing, then increasing. So the location where you have a local maximum is here at 0. So the answer should be 0. Thank you.